Let us now return to the electronic problem that we discussed in earlier episodes. For a periodic solid, the Hartree-Fock ground state, phi 0, is a state where the lowest n by 2 energy levels, that is the valence band, are filled, and all higher energy levels, that is the conduction band, is empty. And that's represented by a single determinant wave function of this form. Excitation of an electron from the valence band to the conduction band consists of the simultaneous creation of a hole in the valence band and an electron in the conduction band, and that's represented by a wave function of this form, a determinant of this form. And in diagrammatic rotation, we can represent that as a hole in orbital I in the valence band and an electron in orbital M in the conduction band. And such an electron-hole pair is now an exciton. Let us now present the rules for such diagrams, and that will allow us to associate a diagram with each integral that we need to evaluate. So electron lines are labeled M, N, etc. and are directed upwards. Hole lines are represented I, J, etc. and are directed downwards. The dynamical operators are represented by horizontal interaction lines with attached electron and hole lines, and these lines emanate from vertices. Each vertex represents the action of an operator on the individual electron or hole. Solid, dashed, etc. lines, interaction lines refer to different operators. All the electron creation and hole annihilation operators lie above the interaction line. Thus, an exciton creation is represented by this diagram, and all the electron annihilation and hole creation operators lie below the interaction line. Thus, an electron-hole annihilation or de-excitation is represented by this diagram. We define the normal ordered form of an operator product as one where the creation operators appear to the left of the annihilation operators. It's all the creation operators appear to the left of the annihilation operators, so that when this operator operates upon this operator product operates upon a ket, the annihilation operators will operate first and then the creation operators will operate. So then the Hamiltonian in the normal ordered form is given by the Hamiltonian projected onto the Hartree-Fock ground state plus the sum of the single particle terms plus, which we call F, plus the sum of the two particle terms, which we call V. We define then the correlation operator HC as the full Hamiltonian minus the projection onto the Hartree-Fock ground state. So that's HC is equal to F plus V. Then the expectation value of HC is the exact non-relativistic energy minus the Hartree-Fock energy, which is the negative of the correlation energy as we have defined it earlier. The Fock operator F is then sigma PQ, FPQs, CP dagger CQ. Here in the summation, P and Q are general indices. They include both electrons and holes. We can separate out the electron and hole summations and write the Fock operator in this form, where I, J, etc. are indices for occupied orbitals, M, N, etc. are indices for virtual orbitals. Then the diagrammatic formulation of the Fock operator is given by these four diagrams. The first one represents an electron undergoing the interaction FMN. The second diagram represents a hole undergoing the interaction Fij. The excitation level in both of these are 0. The third diagram represents the annihilation of an electron-hole pair, and that the excitation level is therefore -1, whereas the fourth diagram represents the creation of an electron hole pair, or creation of an exciton, and therefore the excitation level is +1. From the two-particle part of the Hamiltonian, we get these 9 diagrams. The first diagram represents electron-electron interaction of an electron at this site with an electron at this site. The second diagram represents hole-hole interaction. The third diagram represents annihilation of an electron-hole pair at this site and creation of an electron-hole pair at this site, that is, exciton hopping. For all of these, the excitation level is 0. For the fourth diagram, represents interaction of an electron at this site with the annihilation of an exciton at this site. So the excitation level is -1. The fifth diagram represents interaction of a hole with annihilation of an exciton. Again, excitation level -1. The sixth diagram has excitation level +1 because it represents interaction of an electron with creation of an exciton. And the seventh diagram represents interaction of a hole with creation of an exciton. The eighth diagram represents creation of 2 excitons, and thus excitation level of +2. And the last diagram represents annihilation of 2 excitons, or excitation level -2. We now present the cluster operators. T1 equals sigma mi tim cm dagger ci, which is represented by this diagram, that is the representing the creation of an exciton, and thus an excitation level of +1. T2 is given by quarter sigma imjn timjn cm dagger cn dagger cicj, or creation of 2 excitons and excitation level of +2. T3 is given by this, that is the creation of 3 excitons and excitation level of +3, but we won't need that. The cluster operator is then defined as T equals T1 plus T2. The coupled cluster ansatz is then that the full correlated wave function psi is obtained from the Hartree-Fock ground state phi 0 by operating upon it with e to the power t, where t is the cluster operator. Okay. To derive this expression, we just have to note that e to the power t is 1 plus t plus half t squared plus 1 upon factorial 3t cubed plus 1 upon factorial 4t to the power 4 plus etc. This is the expansion of the exponential, where t is here the cluster operator. We now define the transformed Hamiltonian ht as e to the power minus t hc e to the power t. Then the negative of the correlation energy is given by bra psi hc psi ket, or bra phi 0 ht phi 0 ket, or in other words, the coupled cluster energy is given by the expectation value of ht in the Hartree-Fock basis. Okay. We can note here that all single excitations, double excitations, triple, etc., multiple excitations are orthogonal to ht phi 0. We recall now from the linked cluster theorem that non-zero contributions to the energy and properties come only from the connected diagrams. The Hamiltonian can then be written as ht equals the connected part of hc plus hct plus half hct squared plus 1/6 hct cubed plus 1 upon 24 hct to the power 4, where the expression on the right hand side includes only the connected diagrams. This is known as the Baker-Campbell-Hausdorff or BCH expansion, and due to the structure of the Hamiltonian, the BCH expansion truncates at the fourth order term. So we have here the BCH Hamiltonian and the cluster operator. The coupled cluster energy is given as bra phi 0 HT phi 0 ket, and if we truncate this to include only the single and double excitations, we get the coupled cluster singles and doubles energy, or CCSD energy, as bra phi 0 the connected part of HCT1 plus HCT2 plus half HCT1 squared phi 0 ket. Note that since the Hamiltonian is in the normal ordered form with respect to the Fermi vacuum, Hc does not contribute to the expectation value. That is, the first term in the BCH Hamiltonian does not contribute because Hc is this, and since all creation operators appear to the left of the annihilation operators, these annihilation operators operating on phi 0 will give 0. Okay? These annihilation operators operating on phi 0 ket gives 0, and therefore Hc does not contribute to the expectation value. We first evaluate the terms linear in T1, that is bra phi 0 connected part of HCT1 phi 0 ket, which is equal to bra phi 0 connected part of F plus V times T1 phi 0 ket. Since T1 has an excitation level plus 1, we have to use the terms in the Hamiltonian which have excitation level minus 1. Since we are projecting onto phi 0 the Hartree-Fock ground state, the final diagram must not contain any external lines. That is, we have to close all the loops. Thus, the only diagram in the Fock operator F which can be combined with T1 is this, without leaving external lines, and that gives us this diagram, which is sigma im Fim Tim. The two particle part, that is bra phi 0 connected part of Vt1 phi 0 ket, gives us this, where this part comes from V and this part comes from T1, and here we have the annihilation operator operating on the Hartree-Fock ground state phi 0 ket, and that will give us 0. Okay, so the two particle part vanishes, and therefore we have bra phi 0 connected part of HCT1 phi 0 ket gives us this diagram, which is sigma mi Tim Fmi. Before we go on to the other terms, let us summarize the rules to evaluate diagrams. Each operator interaction line contributes to the final matrix element. The Fock matrix elements are constructed by the rule bra out F in ket, where out and in are the outgoing and incoming directed lines at the interaction line's vertex. In our case, the Fock matrix contribution is Fim. The amplitude is constructed using the whole and particle lines from left to right, first whole then particle indices. In our case, the amplitude contribution is Tim. The sum over all the internal indices, that is, over all the loops. The sign of the diagram is determined via the formula minus 1 to the power the number of holes plus the number of loops. Each such pair of equivalent lines, that is, lines beginning at the same interaction line and ending at the same interaction line, contributes a prefactor of half. For n equivalent vertices, the prefactor is 1 upon factorial n. Coming to the terms linear in T2, that is bra phi 0 connected part of HCT2 phi 0 ket, T2 has an excitation level plus 2. So it has to be combined with the term of the Hamiltonian which has excitation level minus 2, and that is this diagram of V, which corresponds to annihilation of 2 excitons. Combining that with T2 gives us this diagram, which is following the rules we have enumerated: quarter sigma ij mn Timjn bra ij mn ket. Now it is the expectation value of the connected part of Ft2 which vanishes. because that is gives us this comes from F, and sorry, this comes from F, this comes from T2, and now we have these annihilation operators operating on phi 0 ket, which give us 0, and therefore bra phi 0 connected part of HCT2 phi 0 ket is equal to quarter sigma ijmn timjn bra ijmn ket. We are left with the term quadratic in T1, and the non-zero contribution from that term comes from the two-particle part of the Hamiltonian. Thus, bra phi 0 connected part of HCT1 squared phi 0 ket gives us this diagram, which, using the rules we have enumerated, gives half sigma ijmn tim tjn bra ijmn ket. Thus, the final expression for the CCSD, or coupled cluster singles and doubles energy, is given by the sum of these three diagrams. This is the term linear in T1, this is the term linear in T2, and this is the term quadratic in T1. So we see how we can relate the diagrams to the integrals that we need to evaluate, and this gives us a great simplification in the evaluation of the terms. The advantage of coupled cluster over configuration interaction is that it gives a faster convergence to the full CI limit, and also it is size consistent and size extensive. In a configuration interaction expansion, there is no guarantee that if we include, say, 1 million more configurations, that we will get a corresponding improvement in the accuracy. Whereas in coupled cluster, the excitations are included in a more systematic manner, and this gives a faster convergence to the exact answer, and also it gives a better scaling with the number of electrons in the system. Okay. We'll stop here for now.